Hello everyone, and welcome to this explainer. So, today is July 2nd, 2026, and we are going on an absolutely incredible journey under the hood of next-generation UAVs. We're going to look way past standard consumer technology and expose the hardcore military-grade engineering that allows these complex flying machines to operate in, honestly, some of the most unforgiving environments on the planet. I am absolutely thrilled to unpack this structural and technical DNA with you today.
Okay, let's dive into this. The skies today, they are not friendly. We're talking about airspaces completely flooded with intense electronic warfare, extreme weather, and highly hostile countermeasures. To survive all that, a drone can't just be a camera with wings anymore. It basically has to be a highly resilient, flying supercomputer. So before we build this machine layer by layer, we really have to understand that every single nut, bolt, and line of code is designed for one ultimate goal, and that is absolute survival.
Here is our engineering blueprint for today. We'll cover system architecture and certification, UAV power propulsion cores, flight control and comms, extreme environment testing, stealth and electronic warfare, and wrap up with future development and AI.
Let's kick things off with Section 1, System Architecture and Certification. You see, as drones have become more and more autonomous, software complexity has literally skyrocketed. And that brings us to the DO-178C and DO-254 standards, which are basically the aviation industry's golden rules. They mandate 100% traceability. Now, why does this matter? Well, every single line of code and every hardware logic gate, like an FPGA or ASIC, must trace directly back to a specific system requirement. For the absolute highest risk systems, what engineers call DAL-A, they have to structurally test every independent logic condition perfectly. It's a process known as MC/DC. Basically, it guarantees that a random freak glitch won't cause a fatal crash when the drone is flying over populated areas or active front lines.
Let's move along and see how this builds from a modular perspective. Modern drone architecture stacks up in 5 distinct layers. Layer 0, that's your physical carbon fiber and power systems. Then, Layer 1 handles real-time flight control, running rock-solid platforms like Ardu Pilot or ROS-2. Layer 2 brings in edge computing, using advanced neural networks, like YOLO V11, to actively process what the camera sees. Layer 3 is the mission system, which runs the tactical decisions. And finally, the top, Layer 4, handles secure mesh communications and swarm coordination. It's a brilliant setup because if one layer fails, the architecture is designed so the rest of the system can attempt to safely recover the vehicle.
Moving right along to Section 2, UAV Power Propulsion Cores.
Looking purely at the engineering case studies for propulsion, we can see 3 dominant power strategies in play today. First up, internal combustion. Take the MD-550 engine in the Shahed 136, for example. It uses cheap, highly energy-dense liquid fuel to hit a massive 2,500-kilometer range while carrying heavy payloads. Then, you have pure electric systems, like in the Lancet 3. These offer super high burst torque for sudden maneuvers and incredible acoustic stealth. I mean, you barely hear them coming. Third, we have hydrogen fuel cells, seen in platforms like the Raybird. This kind of merges the best of both worlds, giving you a massive endurance of over 15 hours while keeping the drone's thermal signature incredibly low.
If we zoom into the micro details of electric propulsion, we find staggering advancements in battery tech. This number right here, 60 amps, represents the continuous discharge capability of the Molicel P50B high-discharge lithium battery. That is a real game changer. It means the drone has this enormous pool of instant power to draw from for extreme tactical maneuvers. Think about a sudden, violent vertical climb to dodge an obstacle, all while generating significantly less internal heat.
On the other hand, if you need a drone to fly literally all day without giving away its position, a hydrogen PEMFC, or proton exchange membrane fuel cell, is your answer. But honestly, it is an immense engineering challenge. Hydrogen molecules are incredibly tiny, so storing high-pressure gas at minus 70 degrees Celsius requires these highly specialized, low-permeability carbon fiber tanks. You have to prevent the material from becoming brittle and leaking. The payoff, though, because a hydrogen fuel cell only emits water as a byproduct, the drone gives off basically zero heat. That makes it an absolute ghost to enemy heat-seeking missiles.
Let's jump into Section 3, Flight Control and Comms.
To build a truly uncrashable brain, engineers have to solve the problem of single-point failures. Think about it. If you have 3 identical chips running the exact same flight control software, a single compiler bug could crash all 3 at the exact same time. Total disaster. So they use heterogeneous hardware. This brilliantly prevents common mode failure by mixing completely different chip architectures, like putting an ARM processor right next to a dissimilar RISC-V processor. They run side by side, literally voting on every single movement the drone makes. If one crashes due to a bug, the completely different backup instantly takes over without missing a beat.
Now, usually a drone relies on precise dual GNSS RTK satellite positioning. But what happens when that GPS signal gets jammed? It has to rely on its internal sensors. The problem is, at high altitudes, temperatures plummet, and freezing sensors start to drift, which feeds bad data right into the brain. To fix this, engineers actively heat the inertial measurement units, or IMUs. Keeping these sensors at a perfect, constant temperature allows the EKF2 sensor fusion algorithms to flawlessly calculate the drone's exact position using dead reckoning. So even when satellite navigation is completely denied, it knows exactly where it is.
To survive intense electronic warfare, the drone's entire nervous system has to be unjammable. It uses Mavlink V2 for encrypted command telemetry from the ground. Internally, all the drone's parts talk to each other over a jam-proof SIFL or drone CAN bus. Then, to process massive amounts of camera data for AI targeting without any delay, it runs on an ultra-low latency XRCE DDS protocol. And, to prevent the enemy from jamming the signal in the first place, it uses FHSS, Frequency Hopping Spread Spectrum, which rapidly hops frequencies thousands of times a second across the radio spectrum. Try jamming that.
Up next is Section 4, Extreme Environment Testing.
So how do we know these things actually work? Engineers prove these machines can take a brutal beating using strict MIL-STD 810H testing. And I mean brutal. They drop the air pressure to simulate 6,500-meter altitudes. They subject the drone to violent thermal shocks, swinging from -40 degrees to +57 degrees in seconds. They use sign-on random vibration tables to replicate extreme turbulence and engine shaking. They blast it with rain, sand, and highly corrosive aviation fluids. Basically, if it survives all of this in the lab, it can definitely survive the battlefield.
What you should really take away from this is that failure is heavily accounted for. Under MIL standard 461G, specifically the CS117 standard, the drone is actually blasted with indirect lightning strikes. This ensures its electronics won't fry in a massive storm or under an electromagnetic weapon attack. And hey, if every single system completely collapses, an independent, galvanically isolated circuit, meaning it operates on completely separate physical power, deploys an ASTM standard emergency parachute to safely recover the hardware and prevent it from crashing into people below.
Let's look at the armor. Section 5, Stealth and Electronic Warfare.
True stealth operates in 3 dimensions. For acoustic stealth, special notches on the propellers break up noisy air vortices. For thermal stealth, highly advanced wavelength selective thermal regulators, or WSTR, and C/CC ceramic matrix exhaust actually manipulate thermodynamics. They vent heat into the atmosphere at specific wavelengths that enemy thermal cameras simply cannot see. Finally, for electromagnetic stealth, the drone is wired using 360-degree star grounding. This creates a complete Faraday cage that prevents internal computer noise from leaking out and being detected by enemy radio scanners.
Now, what's really interesting here is the impact of those acoustic propeller notches. By utilizing double-slot, double-depth, or DSDD designs on the edges of the propellers, engineers are able to cut the perceived acoustic noise of the drone by over 50%. And the best part? It only costs a minuscule fraction of aerodynamic power loss. Half the noise for almost no penalty. That is engineering at its finest.
But you know, when electronic jamming gets too intense for even the absolute best radio hopping algorithms, engineers resort to a fascinating, low-tech, yet highly effective solution: physical glass. Yep, some modern drones literally unspool up to 20 kilometers of fiber optic wire as they fly. Because the control signals travel as light through a physical glass thread, it grants the drone absolute zero-latency immunity to literally any electronic jamming the enemy throws at it. It's a brilliant mix of old school and cutting edge.
Finally, Section 6, Future Development and AI.
The future of drone warfare is really a rapid iteration loop. Imagine the enemy shifts their jamming frequencies at hour 0. Within 12 hours, Edge AI analyzes this new threat data from the surviving drones. By hour 24, engineers use agile development to write brand new anti-jamming code. And by hour 48, those updates are beamed over the air to thousands of drones sitting right there in the field. It is a blindingly fast software arms race.
So the absolutely crucial point here is how this tech is fundamentally changing operations through MUMT, or manned-unmanned teaming. We are shifting away from a single pilot flying a single drone. Instead, we're entering an era of 3D combat networks. Picture a few human commanders safely at the rear, directing vast, decentralized AI drone swarms. These swarms share sensor data, identify targets, and make real-time tactical decisions cooperatively. As we wrap up this explainer, we are left looking at a marvel of modern engineering, a machine forged in extreme environments, wrapped in stealth, and powered by highly advanced artificial intelligence. But as these decentralized swarms learn to navigate, target, and strike with less and less human input, we have to ask a pretty profound question. When machines make the decisions at the very edge of the battlefield, where does the human ultimately fit in? Thank you so much for joining me on this deep dive. Keep learning, keep questioning, and I will catch you in the next one.